All right, so today is the third lecture in our first part of the class on complex analysis. So there's going to be 3 more lectures next week, and I would say the next week is going to get pretty interesting. We're going to learn how to solve some really, really nasty integrals that you probably never thought you would be able to solve without Mathematica. Now, the importance of solving interesting and difficult integrals is something I'll have to motivate and explain kind of in detail next week. But for now, just take my word for the fact that there's lots of things you want to integrate. And knowing something about analytic functions in the complex plane allows you to integrate a lot more stuff than you learned in calculus class. Okay? So this is like calculus on steroids at this point. Okay, I just want to show you homework 1. Homework 1 is out, and it's due next Friday. This homework it might look a little bit long. It is a little long because it's a 2-week homework. But the first 3 problems are actually super simple. Okay, so for example, I want you to take these 3 expressions and just write them as a plus bi, where a and b are real. Easy. Find all of the solutions of these equations, e to the z equals 1, e to the z equals I, e to the z equals I plus 1. Just a quick question. How would you go about solving that general type of equation for z? Right, you would essentially take the log of both sides. And how many values of the logarithm are there? Yeah, how many z's are there such that log of z equals z equals log of 1? Infinitely many, right? Because for every angle of z, you can add 2 pi or subtract 2 pi as many times as you want. So this is an easy problem. Find all of the solutions of these. Z to the 4th equals minus 1, z to the 3rd equals 8i, z to the 5th equals 1, right? This is what we did last lecture. I would encourage you to try and do as much of this homework as possible, as soon as possible, because this is actually going to motivate a lot of what we're going to do next week, especially the second half. I'm going to skip all this stuff. You're going to do things like find whether or not a function is analytic using the Cauchy-Riemann conditions. You're going to find all possible analytic functions such that the real part is x squared minus y squared. The 2 most interesting problems are 1,7 and 1,8. And so what I want you to do here is we're actually going to start thinking about contour integrals in the complex plane. Okay, that's what we're going to do in the second half of today, and all of next week are contour integrals in the complex plane. And so this is a nice simple contour integral where if you plug in this parameterization for z, so if you integrate around a big circle with fixed radius, you can analytically solve this contour integral. And this is going to motivate a lot of what we're going to do next week. And for this last problem, you're actually going to write a script in MATLAB to compute the contour integral. And you're going to verify some of the properties that we're going to derive today and on Monday. Okay? So it's not a terribly difficult homework, but it does have a lot of parts. And if you could get through all of this, or at least look at all of them by the end of Monday's lecture, that would be kind of the right time frame to be keeping up with the material next week. Any questions? Okay. I think that's it for the computer. Okay. All right, so I'm going to do a couple of things today. So first, we're just going to summarize what we did in the last lecture, which is we got to the Cauchy-Riemann conditions. We're going to use the Cauchy-Riemann conditions to show that the logarithm function is, in fact, a nice analytic function. And then we're going to start looking at contour integrals in the complex plane. Okay? So from last time, so we had these special functions which are called analytic functions. And the basic idea of an analytic function is that you can take the derivative of analytic functions at points where that function is analytic. Okay, you can take the derivative, and it doesn't matter how you take the limit, as delta z goes to 0. In the real part or the imaginary part, the derivative still exists, and it's equal. And so we derived these Cauchy-Riemann conditions. And these Cauchy-Riemann conditions tell you when a function is going to be analytic. Okay, so if I have f of z equals u plus iv, so u is a real valued function, v is also a real valued function, then f of z is analytic if and only if, two f's means if and only if, the following conditions hold. We have partial u, partial x equals partial v, partial y, and partial v, partial x equals minus partial u, partial y. Okay? So this is a really nice, simple formula that allows us to check whether or not a function is, in fact, analytic. Okay? And we essentially derive these conditions by taking our function f and computing the derivative at a point z and taking the limit both in the real direction and in the imaginary direction separately. And these are the conditions that have to be true if those derivatives equal each other. Okay? So this is a statement of the fact that this has derivatives which exist at points z, where f is analytic. So why don't we just do a couple of quick, easy examples. So I told you that all polynomials are analytic, right? Polynomials are analytic, sine and cosine are analytic, e to the z are analytic. Anything that has a convergent Taylor series expansion is analytic. And anything that's analytic has a convergent Taylor series expansion. That's very, very important. Let's just take this simple function z squared. So how do I get u and v for this function? What's the first step? Sorry? Yeah, I just plug in x plus iy, and I FOIL it out. I just expand it out. So this is x plus iy squared, which is x squared minus y squared plus 2ixy. Right? Okay, and this real part is u of x and y, and this imaginary part, 2xy equals my v of x and y. So let's just verify that these Cauchy-Riemann conditions hold for this simple function. So we know that this is analytic because it's literally an analytic expression of z. It's not just a function of x and y. And we're pretty sure we can take the derivative of this function in any direction. So let's just go through the partials. So partial u partial x equals 2x. Partial v partial y equals 2x. Okay, good. The first Cauchy-Riemann condition is satisfied because these two equal each other. Partial v partial x equals 2y. And partial u partial y equals minus 2y. And so the second Cauchy-Riemann condition is also satisfied. Okay, so the fact that these these expressions equal each other means that at any point, and this is also true for any point z, right? Any z equals x plus iy that you name, these are true for any x and for any y. And so this function is analytic and differentiable everywhere. And clearly it has a convergent Taylor series because it's just a single monomial. Okay, so that's like a really, really simple example of how you use these Cauchy-Riemann conditions. So because these are true, this implies that f is in fact analytic. And it's not just analytic at a couple of points in z, it's analytic at all z in the complex plane. Okay, makes sense? So I'm just going to do another slightly more detailed example. So you can You can derive polar coordinate expressions for the Cauchy-Riemann conditions. I thought about putting this on the homework, but I decided it's a better exam problem. So if you had Cauchy-Riemann in polar coordinates, you would have something like, so now we're going to say that z equals r e to the I theta. And we're still going to have f of z equals u, but now this is a function of r and theta, plus iv times a function of r and theta. Right? We can write our complex variable in polar coordinates, and our function still has a real and an imaginary part. And so the Cauchy-Riemann conditions in polar coordinates would read like the following. Partial u partial r equals 1 over r partial v partial theta. And also we have to have partial v partial r equals minus 1 over r partial u partial theta. Are my u's and v's impossible to tell apart? Does anyone have a lot of trouble reading my u's and v's? I used to have a physics professor that would write pressure and density, and it drove me crazy. So my u's always have this little tail. That's how you can tell that they're u's. So these are the polar coordinate Cauchy-Riemann conditions. Okay? And these are useful for demonstrating that certain functions are analytic that are more easily expressed in polar coordinates. So of the functions that we've looked at, what are some functions that are more easily expressed in polar coordinates? Okay, I mean, z squared is actually pretty easily expressed in polar coordinates. So I have an example in the notes for log z. I'll just let you do that like on your own time. Let's just do this example. Okay, so z squared equals r squared e to the 2I theta, right? Okay, and that has a real part r squared cos 2 theta, and an imaginary part r squared sine 2 theta. Okay, so this is my function u, and this is my function v. I'm actually starting to think that this was easier in Cartesian coordinates, but we'll go with it. So what is partial u partial r? Partial u partial r. 2r cos 2 theta. Okay, what's partial v partial theta? It's 2r squared times the derivative of this is cos 2 theta. Okay, so it is true that if I take dv d theta divided by r, I get du dr, right? So that Cauchy-Riemann condition is satisfied, the first one. Okay, partial v, partial r is 2r sine 2 theta, and partial u partial theta is minus 2r squared sine 2 theta. And so this has the same relationship where if I divide this by r and take the negative, I get the top expression. So both Cauchy-Riemann conditions are satisfied in Cartesian and in polar coordinates. Okay, this is not the best example of an easy, something that's easier in polar coordinates, but log is actually a lot easier in polar coordinates. Okay, everyone comfortable with the mechanics of this? So you're going to be doing this for the function e to the z, the exponential function, and also for the function sine of z. And you should also be able to do it for the function cos of z. That might be the kind of thing that would be on an exam. Like I might just give you some functions and ask you if they're analytic or not. Or I might, yeah, that would be something I would do. Okay, so one of the really neat properties of analytic functions is that analytic functions, if a function is analytic, then it is the solution of Laplace's equation. So do you remember what Laplace's equation is? Okay, so let me just write this down. If a function f of z equals u of xy plus I v xy is analytic, then both u and v, so u and v are real valued functions, right? X is a real number, y is a real number, u and v are both real valued functions. Then both u and v solve Laplace's equation. And Laplace's equation is grad squared u equals 0, grad squared v equals 0. This is called the Laplacian operator. And it's, del dot grad of v, something like that. Okay, we looked at this last quarter. Did I already show you the picture of Laplace on the Eiffel Tower? No? It's pretty sweet. All of the people that were studying in complex analysis, like more than half of them are on the Eiffel Tower. Their names are forever ingrained on the Eiffel Tower because French people honor their mathematicians, and they had a lot of really, really great ones. Okay, so I'm going to show you why this is true. So essentially what we're going to do is we're going to take the Cauchy-Riemann conditions and take additional derivatives of them. So Cauchy-Riemann 1 is partial u partial x equals partial v partial y. And Cauchy-Riemann 2 is partial u partial y equals minus partial v partial x. And so what I'm going to do is take the partial of both sides of this with respect to x and with respect to y. So partial partial x, partial partial y. And we get something like partial squared u partial x squared equals partial squared v partial x partial y. And down here we get partial u partial y squared equals minus partial v partial x partial y. Simple. I just took the derivative of both sides. I'm like making stuff up here. I just took the derivatives. But what I can do is I can actually equate, because I have a partial squared v partial x partial y, and I have the same thing here but negative. I can essentially equate equal and opposite parts of the left-hand side. So what this means is that partial squared u partial x squared equals this thing. And this thing equals minus partial u squared partial y squared. Okay? And so what that means is that I have partial squared u partial x squared plus partial squared u partial y squared equals 0. And this is just the longhand form of Laplace's equation. This is just del squared u equals 0. So if the Cauchy-Riemann conditions hold, meaning f is analytic, and I'm basically assuming that if f is analytic, then I can take any higher derivative I want and all partial derivatives, that's fine. Then I can essentially take partial derivatives, and through this mixed partial term, I can equate the partials with respect to only x and the partials with respect to only y, and I get this nice cancellation so that they have to equal 0. You also can do the exact same thing starting with the second. How do I do this? You can also do the same thing. Yeah, you can just take the other partial. So you could take the partial of this Cauchy-Riemann 1 with respect to y and the Cauchy-Riemann partial with respect to x, and you can add up those terms and you can get the other Laplacian, which is partial squared v partial x squared plus partial squared v partial y squared equals 0. This also has to be true. So this is really special. What this means is that now we have a nice way of finding solutions of Laplace's equation. Okay, so for every analytic function you can name, so for z squared or sine of z or e to the z, all of these analytic functions, the real part and the imaginary part both solve Laplace's equation. And Laplace's equation is really, really important. For example, Laplace's equation would tell you what the infinite time temperature distribution is on a surface, or what the gravitational potential is in all of 3 space, or what the Coulomb potential field looks like. This is an extremely important set of equations, the Laplace equation. And now we're starting to realize that the real and the imaginary parts of analytic functions always solve Laplace's equation. Very, very interesting. And they're related. The real and the imaginary parts are related via these Cauchy-Riemann conditions. So these are so special that they have a name. So U and V are called harmonic functions. And if you look in the course catalog at almost any major university in the math department, you'll find an entire grad class on harmonic functions. Don't recommend you taking it unless you really, 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 really like complex analysis. But these are really important functions. They solve lots and lots of PDEs that we're going to look at in a week or two. Okay? Okay, are there any questions about what we've been doing with harmonic functions or how to analyze these systems or what it means to be harmonic? Because this would be the time to take a step back and reflect on things for a few minutes. So what are some examples of functions that are not analytic? What is it? So what it means to be analytic is that a function is smooth. You can take the derivatives. The derivative means what you think it means. So if I look at a nice rolling hill, and I think of that nice rolling hill is kind of like an analytic function, right? The derivative exists at every point. And I could take the second or the third or the fourth derivative. They're nice and smooth. It's like what we are used to thinking about. Z squared, z to the fourth minus z squared, sine of z. All of these nice, smooth, well-behaved functions that you can do calculus on are analytic. So what's an example of something that's definitely not analytic? Sorry?
Modulus function.
Okay, the mod function, something that's discontinuous. Let's think of an example that's easier to visualize. 1 over z. So 1 over z is a good one. We essentially have, I can't really draw this, but in the complex plane, we're going to have something that looks like a black hole, right, at z equals 0. It goes down to negative infinity, right? Actually, probably not. Maybe it goes up to positive infinity too. And maybe you should flip my board. But these things go to positive and negative infinity depending on what your real and imaginary parts are. So definitely discontinuous. The derivatives definitely equal different things, kind of epsilon to the right or epsilon to the left or epsilon in the plus or minus I directions. 1 over z is a nice example that's messed up. I'm thinking more, what I drew was log of z. So log of z looks more like a black hole, where you go down to negative infinity at 0. So that's a good example of a function that definitely is not analytic at z equals 0. 1 over z is not analytic at z equals 0, but it is analytic away from there. I think you should be able to calculate the derivative away from z equals 0. What are some other examples? Like, what's the basic feature that we're starting to see here? Singularities. Okay, so division by 0. Anytime I have a division by 0, I lose analyticity in some small neighborhood around that point. I'm kind of jumping the gun. I'm telling you stuff that is from next week, but I want to do this because I want you to be thinking about examples of nice functions and examples of tricky functions. So you have singularities, which basically just means, divide by 0, so something that blows up to infinity. In the complex plane, these are called poles. Don't ask me why. Examples are like 1 over z, or log of z, or 1 over z squared, things like that. And these functions are not analytic. What are some other examples of things that are not analytic, that don't have singularities? Step functions. So I was thinking on the way over here of an example, and I'm thinking of like the cliffs between Texas and New Mexico. Right, there are some step cliffs where you have high plains. This is like where Wile E. Coyote lives. I can't really draw that well. And so you could walk up here on this part to the end of the cliff, but then you'd have to fall all the way down to walk down here on the bottom. Okay, so this function is analytic here and analytic here, but it's not analytic on the boundary of these two steps. There's no singularity, but it's just discontinuous. The derivatives don't exist at that point. Okay, so what I'm trying to do is essentially just build your intuition for the fact that these analytic functions are not anything magical or mystical or crazy. The Cauchy-Riemann conditions are just nice ways of testing that these things don't happen, that you don't have singularities, that you don't have steps in the cliff, that you can compute derivatives. Okay? And what we're going to find is that there are some really important functions that do have isolated singularities. All of these singularities are, for example, isolated at the origin, z equals 0. If I wanted, I could create something with a singularity 1 over z minus a, and now I have a singularity at a. Or I could have log of z minus a. Now my singularity is at a. That's fine. And we're going to figure out how to integrate around functions that are analytic, that are nice. And we're also going to find out how to integrate in contours around nasty non-analytic functions, around singularities. So that's kind of what we're going to be doing in the next week, and we're going to start now. Any questions about this, what it means to be analytic? You have lots of time to think while I erase the board.
Harmonic functions, if it's analytic over the entire domain, is that the only case that they're harmonic? Or if it's analytic over most of the domain, is it harmonic over a domain?
That's a good question. So those functions u of x and y will satisfy Laplace's equation at any points x and y where our original function was analytic. So if there's some domain of analyticity, then that would be the domain under which those functions u and v are in fact harmonic. Yeah, so you can have like restricted domains where they're harmonic. That's actually a nice segue into what we're going to be talking about. So let's say that I have a function. Okay, so say f is analytic on a domain D. Okay? Now, I'm going to use this a lot. This is kind of an abstraction, and I'll tell you what I mean in a little bit. But the basic idea is that I have this nice blue area in the complex plane where f is well behaved. So this is my complex plane. This is the real part, x, the imaginary part, y, and this is the complex plane. This is my domain D in blue. And outside of this domain, I might have some really nasty stuff. I might have lots of poles and singularities. These might all be black holes. Okay? But here, my function's nice and smooth and analytic. Yeah?
Is the domain simply connected or multiply connected?
So for now, I'm going to say that D is a simply connected domain. And what that means is that it doesn't have any holes in it. Okay, this is a topological. So there's a lot of topology in advanced complex analysis, but the basic idea is that simply connected is something where it's a blob, like it's one blob with no holes in it, and you could continuously deform it away, as opposed to something like a donut, which is not one single blob. It does have a hole in it. And any way that you try to continuously deform this donut, you're still going to have a hole in the center. There's no way to get rid of it. Okay? So we don't want these. This is simply connected. And you can have really weird shapes that are simply connected. I can have something that snakes around. That's simply connected. This is topologically the same as a circle, not a donut. This doesn't have any holes in it. I could deform this in Play-Doh and have one big spherical blob, as opposed to this, where there's no way to deform that without smashing the hole away. Okay, good question. So this is a simply connected domain. Okay, and so we're going to start thinking about how to do contour integrals in the complex plane. How many of you have seen Laplace transforms before? Okay, did you use Laplace transforms to solve ODEs, PDEs? Okay, so how many of you remember how to compute the inverse Laplace transform? Is it a lookup table or is there a formula for it? Sorry? So most of us use tables, but it turns out that there is this integral in the complex plane. So you integrate over this big contour, C, and there's probably a bunch of nasty poles that you're integrating around, a lot of weird singularities and stuff. And so, for example, we want to be able to integrate functions in the complex plane because it's going to allow us to compute inverse Laplace transforms. That's, if it wasn't for Laplace transforms, I would not be telling you about complex analysis, period. I thought about it. I thought, how can I get away with not teaching complex analysis? But I realized I really want you to understand where Laplace transforms come from and how they originate and how to compute these integrals because they're so important in partial differential equations. Fourier transforms too. Okay, so what we're going to do is we're going to take a function f and we're going to start integrating it over contours C. And so let me just draw this contour C. So first I'm going to draw a path from Z1 to Z2, and I'm going to call that contour 1. Okay? So what we're going to do is we're going to integrate over this contour f of z dz. And integrating contours in the complex plane is actually not super complicated. I just take f and I write it as real plus imaginary part. I take dz and I write it as real plus imaginary part, and I expand them out, and I get u plus iv times dx plus I dy equals u dx minus v dy plus I times v dx plus u dy. U dy plus v dx. This is all under the integral. Okay, this isn't too complicated at this point. I just took my function and my differential dx and I multiplied them out and I isolated them into real and imaginary parts. There's basically two tricks in all of complex analysis. You either expand things in real and imaginary, or you write them in polar coordinates as r and theta. Those are the two things that we always go to, and you just see which one gives you something that looks nice. Okay? So what I'm going to tell you, I'm going to say that it's a theorem, but I don't think we're going to prove it. But it's important. This is just a fact. When I say theorem, this just means that there's a fact that you can use. A usable fact is that if f is analytic in D, and D has those nice properties that's simply connected, closed region, it doesn't have any holes in it, then the integral of f of z dz is independent of path. It's independent of the path that I took to get from z1 to z2. So for example, I could have taken a totally different path from z1 to z2. I could have taken c2. And as long as c1 and c2 both live inside of this nice, simply connected analytic domain D, then both of these integrals are equal to each other. I haven't told you why yet. I'm about to tell you why. So what we have is, integral of c1 f of z dz equals integral of c2 f of z dz. Pretty interesting, okay? What are some other systems we've looked at where this type of thing is true, where the integral doesn't depend on the path? Conservative vector fields, right? So if I take a 50-pound mass and I climb it up a hill, my potential energy change it's going to be the same no matter which path I take up the hill, as long as I go from the same height 0 to the same height 1. Okay? That's an example of a conservative vector field. And the idea is, you can read about the details in my notes, but the basic idea is that both of these are what are called exact differentials if my function satisfies the Cauchy-Riemann condition. So these are called exact differentials. How do we think about this? It basically means that there is some function big F of x and y plus big I of g of x and y, where this is the derivative with respect to x and the derivative with respect to y of f. And same thing with respect to g. So like u equals f sub x. This sub x means partial x. V equals minus partial f partial y. And we also have u equals partial g partial y and v equals partial g partial x. Now remember that u and v satisfy Laplace's equation. What other systems did we look at last quarter that satisfied Laplace's equation? The potential flow and potential functions, right? The gravitational potential function was an example of a real valued f, so that if I took partial f of x and partial f of y, then I would get functions that satisfied Laplace's equation. So you can think of this as a complex potential. Okay, and grad of f gives me my vector field, the u component and the v components. Or grad of g gives me my vector field. Okay, so I'm going to go a little bit fast past this. There are things you can do to convince yourself that this is true. What I want you to know is that this is a very, 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 very important fact. If I have a function which is analytic in a domain D, and I'm going to take the integral from some point z1 to some point z2, it doesn't matter how I take that integral, what path I take at all. That's the fact that matters. Okay? And so there's a really important ramification of this called the Cauchy-Goursat Theorem. I haven't checked and seen if Goursat is on the Eiffel Tower, but he probably is. So the Cauchy-Goursat theorem. So are there any conclusions that you can draw immediately from the fact that the integral over C1 and the integral over C2 are equal to each other?
Start at Z1 and end at Z1 equals 0.
Yeah, exactly. If I start at Z1 and I end at Z1, then that integral should be 0 regardless of the closed contour that I take. Okay, that's the Cauchy-Goursat theorem. So it's all the same stuff. If f is analytic over D, blah, 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 blah. So if f dot, 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 analytic over a simple closed curve in a domain D, then the closed integral of f of z dz equals 0. And I'm just going to draw this picture so that you have it. You have some curve starting at z naught and ending at z naught. And this entire curve lives inside of a nice, well-behaved analytic domain D. It's analytic everywhere here. Then this closed contour integral always equals 0. Okay. You can prove this using Green's theorem. And I'll get you started, and then you can follow the rest of it. This is the kind of thing that might be an exam problem. So if you wanted to prove this, then you would say, OK, I'm going to take this expression here. So I have integral over this contour of u dx minus v dy plus I times the integral of u dy plus v dx. And I can use Green's theorem to turn these contour integrals into surface integrals on the entire internal area of this red curve. Right? This is some surface S. And by Green's theorem, by Green, this equals some double integral over S of minus partial v partial x minus partial u partial y with respect to dx dy. And then there's an equivalent imaginary part plus I times the double surface integral of partial u partial x minus partial v partial y over dx dy. Now, what can I say about these sets of partial derivatives? Sorry? Why are they equal to 0?
Because they satisfy the clauses.
Because those are the Cauchy-Riemann conditions. Each of these integrands has to equal 0 when f is analytic. Which is why this is only true if the entire curve lives inside of an analytic domain D. Okay? So we're starting to get some really, really interesting results here. Okay, if I do a closed contour integral over any complex function in a domain where it's analytic, then that closed contour integral equals 0. So in the homework, you're going to actually do a MATLAB example where we're going to code up like sine of z. And we're going to do this closed contour integral of sine of z, and we're going to show that we get 0. Okay? Okay, I'm going to show you one geometric sketch before the end of class. And then I think what I'm going to do next lecture, so on Monday, I'm actually going to code up in MATLAB this contour integral, and I'm going to show you examples of where this equals 0 and where it doesn't equal 0. And we're going to start thinking about what happens. What if I dropped a couple of singularities in the center of this contour integral? What if D wasn't simply connected? What if it was like a donut and there were some weird singularities in here? How does this integral formula change? Okay, that's where we're going, is we want to be able to integrate systems that are mostly analytic, but they have a few singularities in them. But don't worry, we'll get there in due time on Monday. Okay, so the idea in this picture that I want to draw is that inside some analytic domain D, so we're analytic everywhere in this domain D, then if I have two contour integrals, I can essentially deform this contour into any other closed contour integral I want. So C1 and C2. I mean, of course, these are equivalent because they both integrate to 0. Okay? But this is also true. Let's see if I can draw this. It's also true in an analytic domain like this. Okay? So these integrals over C1 and C2 are obviously equal because they both equal 0, right? So integral of C1 of f equals integral of C2 of f, but duh, of course they equal 0. They both equal 0, right? But in this case, the same thing is true. C1, C2. C1, so here the same thing is true. Integral over this contour C1 of f equals integral of contour of C2 of f. But here they do not equal 0 because I have some weird singularities in here. The Cauchy-Goursat theorem that we derived doesn't hold here, basically because Green's function is not satisfied inside of here. Those integrals don't equal 0 because I have weird stuff where Cauchy-Riemann is not true in the middle here. And so the picture that I like to draw here is essentially that I can take these two integrals and I can draw a new one. Bear with me, this is not the best art ever. Okay, where this outer one was C1, this inner one is minus C2. And these are infinitesimally close together. These two kind of straight lines, these are epsilon apart. Okay? Now, this red curve is everywhere analytic. And I can draw that simply connected blue thing that I had before here. So D now is simply connected and analytic everywhere here. And the idea is that this closed curve, this closed red curve does have 0 integral. This does satisfy the Cauchy-Goursat theorem because my blue curve is simply connected. So I have this new integral of C1 plus integral of minus C2 plus integral of plus epsilon plus integral of minus epsilon does equal 0 because Cauchy-Riemann is true in this whole blue area and Green's theorem applies, and so the Cauchy-Goursat theorem holds. Now, I said that these two were infinitesimally close to each other, and so they exactly cancel out. And so I have that the integral of C1 equals minus the integral of minus C2. And if you integrate something in the minus direction, that's just minus of the integral in the positive direction. So I have integral of C1 equals integral of positive C2. Even though both of those integrals are finite, they're non-zero. Okay? So this is just an example of the kinds of surgery you can do on the complex plane. I call this surgery because we did an epsilon incision, and we made our blue region simply connected. And then we were able to do this Cauchy-Goursat theorem. These integrals are not equal to 0, but they're equal to each other. So I can deform C1 into C2 as long as both of them live entirely in an analytic domain D. I want you to think about this. This is not super simple. It's not obvious, but it's really important. So think about this. Make sure that you understand every step that we took to get this expression. OK, I'll see you on Monday.